The Ka-Kb relationship for conjugates. Let's look at these two. First of all, are we agreed that these two constitute a conjugate acid-base pair? Recall that the conjugates differ by an H+. Yes, those two are definitely a conjugate acid-base pair. Which one is the acid and which one is the base? We've said that for conjugates, not only do the acid and base of the conjugate pair differ by an H+, but the acid has the extra H+. Therefore, the ammonia acts as a base. It would tend to accept protons, and the ammonium ion would tend to donate protons. So the equations that would apply are as shown. Based on these equations, let's write a Ka and a Kb, that is, let's write an equilibrium constant expression. For which equation, 1 or 2, would we write a Ka for? And that would be equation 2, because in equation 2, ammonium ion is donating a proton. We need to write a Kb expression from equation number 1, where the ammonia is accepting a proton. It's the same old thing, products over reactants for Ka, and for Kb, products over reactants. Again, note that we do not include the water in the equilibrium constant for Kb. You can see that water is absent, and that's because we don't write pure liquids or pure solids in an equilibrium constant expression, and the water is a liquid. So let's just see what happens if we took Ka for ammonium and multiplied it by the Kb for its conjugate, ammonia. We've copied the Ka expression right there, and there's the Kb expression. Now we can simplify this a little, because I see we have the ammonia concentration in both numerator and denominator, and we have the ammonium ion concentration in both numerator and denominator, which means Ka times Kb simplifies to be hydrogen ion times hydroxide ion concentrations. That was one of the first things that we ran into when we started talking about acids and bases and calculations related to them. That the product of the hydrogen ion and the hydroxide ion concentrations at 25 degrees Celsius was a constant, 1 times 10 to the negative 14th. So, at that temperature, the Ka times the Kb also equals that same constant. Because they are easily calculated from Ka values, reference tables are often short on Kb values. So to calculate a Kb for a conjugate, if we know the Ka, we simply know that the product of those two is 1 times 10 to the negative 14th. Just like the pH is the negative log of the H ion concentration, the pKa is the negative log of the Ka, and the pKb is the negative log of Kb. And we have one more equation to write down. If H times OH is 1 times 10 to the negative 14th, and pH plus pOH equals 14, well, we just saw in the last slide that Ka times Kb also equals 1 times 10 to the negative 14th, and therefore we can write this equation, pKa plus pKb equals 14 at 25 degrees Celsius. So when we say pH, we mean the negative log of the H. When we say pKa, we mean negative log of the Ka. So the negative log of anything is the P of anything. The negative log of nut would be peanut. The negative log of ch would be peach. The negative log of shooter would be pea shooter. The negative log of kaboo would be pKaboo. The negative log of brain would be pea brain. The negative log of soup. So let's try a problem. For hydrofluoric acid with a Ka of 6.8 times 10 to the negative 4th, let's find all these things. What's the formula, first of all, for hydrofluoric acid? Oh yeah, it's HF. Okay, what does A say? Write the formula of the conjugate base. So the conjugate base would be exactly HF, except it would be short an H+, which means the conjugate base is going to be F-. How about B? Write the equation for which Kb applies. Well, that would be F- gaining a proton from water, which is written as a reactant, forming the weak acid HF and the hydroxide ion. How about letter C? Write the equation for which Ka applies. Well, Ka would be HF donating a proton and also forming the fluoride ion. And part D, let's find the pKa, the pKb, and the Kb. We know what the Ka is. If we know what the Ka is, we can take the negative log of it to find the pKa, 3.17. This little SF football helmet here is my reminder that we are going to use the significant figures rule for logarithms, which says that whenever you take the logarithm of a number, however many significant figures are in that number, your logarithm must have that many decimal places. The number that we took the logarithm of was 6.8 times 10 to the negative fourth. It has 2 significant figures in it. Therefore, we must have 2 decimal places when we report our logarithm. Just didn't want you to forget that. Okay, now let's find the pKb. Well, the sum of those two is 14, and we just figured out the pKa, so the pKb is 10.83. And we have one more thing to find. We have to find Kb, and there are actually 2 ways we could do this. The first way would be that the product of Ka and Kb is 1 times 10 to the negative 14th. Way up at the top we were given what the value of Ka is, so we can calculate Kb to be 1.5 times 10 to the negative 11th. Or, if you are good with logarithms and knowing what they mean, if you take 10 to the negative pKb, you will get the Kb. Let's summarize. 1. For any conjugate acid-base pair at 25 degrees Celsius, the relationship between the Ka of the acid and the Kb of the base is given by that expression there. Their product is 1 times 10 to the negative 14th. 2. Any K and its pK are related by the log base 10, just as pH and H ion concentration, or pOH and OH ion concentration are. These equations hold at any temperature. And you can see I've colored them in maroon there on the right. 3. Finally, also at 25 degrees Celsius only, the pKa of the acid and the pKb of the base are related by the equation their sum is 14.